right. Okay, welcome everybody to our How to Electrify Buildings in Truckee, Tahoe webinar series. We are really excited today to have Eric Bosworth joining us. As many of you know, these webinar series are a partnership put on by CTA, the North Tahoe Chapter of Citizens Climate Lobby, and 100% Renewable Truckee. And we have these webinars posted on the Climate Transformation Alliance website. And so this webinar is also being recorded and will live there afterwards. Today, we will be doing questions primarily at the end of Eric's presentation. So as he is giving his presentation, feel free to put your questions in the Q&A function or in the chat. And then as we get to the end, if you would like to ask your question, feel free to raise your hand and we will unmute you so that you can have a back and forth and some discussion with Eric. Our team will be monitoring the chat and the Q&A, so none of your questions will fall through the cracks here. And I'm going to go ahead and pass it over to Deirdre now to introduce our speaker.
Thank you, Kaylee. We are so pleased to have Eric Bosworth with us today. He is one of the leading experts on thermal energy networks, particularly from the point of view of utilities. Until recently, Eric was the manager of the Clean Technologies Group at Eversource Energy, and his work there included leading the first network geothermal project deployed by a utility in the United States. That's the famous project in Framingham, Massachusetts. He was responsible for oversight of the project from feasibility and site selection through operations, and that project is currently operating. The project has sparked interest from gas utilities around the nation in network geothermal heating and cooling, and it has helped to inspire legislation in several states, including California, to authorize and encourage gas utilities to build geothermal networks to reduce greenhouse gas pollution and also perhaps to move toward changing their business model as we transition to clean energy. Eric is now the principal consultant at Thermal Energy Insights, a company that he has founded, and he provides technical consulting services to utilities, municipalities, government agencies, and private companies on a wide range of energy topics, and of particular interest to us on thermal energy networks. We are interested in hearing about this new venture from Eric and also about what he is hearing from those interested in thermal energy networks around the country and around the world. Eric holds a Bachelor of Science degree in Chemical Engineering from Carnegie Mellon University. And Eric, we are so pleased to host you. Thank you very much. And I'll turn this over to you now.
Thanks for the great introduction, Deirdre. Let me know if my sharing works okay here. I will throw some slides up quickly and start going through those if that works. All righty. As I said, thank you very much for the great introduction. My name is Eric Bosworth, and I am the principal consultant at Thermal Energy Insights, a relatively new venture for me. I've been at it all of 4 weeks now, so hopefully I can take some of that experience from working at the utility and actually upstream in the energy industry prior to that and help deploy it to new and interesting endeavors like thermal energy networks and network geothermal systems specifically. In initial conversations about this presentation, my understanding is that folks here on the webinar probably have a reasonable understanding of what geothermal is, but I always like to start off by walking through kind of the types of geothermal, just because the word has such variety in what it can mean. One person says geothermal and they're thinking the shallow geothermal on the left here. Generally here in the States, that's about 1,000 feet and above to surface. looking at temperatures in the 55-degree range in terms of ground temperatures. But it can also mean a few miles deep, generating supercritical steam for power gen and everything in between. So for the focus of the presentation and the conversation today, I'm going to stick to the left side of this graph, talking about shallow geothermal specifically. That's for heating and cooling loads. And, if folks are interested in talking about direct use geothermal or deep geothermal, I'm always happy to have a conversation about that as well. Coupled with the geothermal aspect of this, there's also the district or the thermal energy network side of it. Don't want to give a full history lesson here, but suffice it to say, we've gone through a few generations and iterations of it, and the general trend on district heating is that the temperatures are getting lower and lower, more towards ambient as we go. They started off with the old distributed steam systems of the late 1800s that were coal-fired. Then we moved to hot pressurized water, then to less hot water, but it was still direct use in that kind of 140-degree Fahrenheit range. Got even lower now, and with fifth generation, what are called ambient temperature loops, we're looking at right in that, probably in the winter 35 degrees at a minimum, in the summer maybe 75, 80 degrees at a maximum. And the real innovation there is that you can both heat and cool with that temperature range. So with fifth generation systems, we've taken a step into heating and cooling, which is extremely relevant because that makes it deployable almost anywhere. If you're looking at areas like Texas that are primarily cooling, they can use a system like this. But then you get up to Canada and the same type of technology works because of that nice ambient temperature range. So all of this comes together into a picture of what is a networked geothermal system or a thermal energy network. And at its heart, it is essentially just a system of water pipes that run through a neighborhood, and you use that water as a medium to distribute thermal energy to customers. So frequently these are coupled with bore fields. So you'll have a series of holes that you drill into the ground. In the case of the Framingham project, we went about 600 feet down. You install a U-bend of plastic pipe down into the bottom of that hole, and then you circulate water through it to either pull heat out of the ground in the winter and move it to the buildings for heating, or you do the exact same thing in reverse in the summer. You pull heat from the buildings, move it to the ground, and then deploy it down into the ground for storage until the next season. The last piece of the picture here is the ground source heat pump. I'll talk a little bit about that in a few slides here, but it's sort of the third leg of this stool in terms of providing the heating and the cooling to the buildings, because as people know, you can't heat very well with 55 or 60-degree water. You need to get it all the way up to 90 or 100 degrees to really properly condition the inside of a building. One other interesting thing that becomes available when you do start building out a thermal energy network is the availability of other thermal assets as well. The geothermal boreholes are great. We know the technology works. Folks have been installing geothermal systems for decades at this point, drilling a hole in their yard or on their property, pulling piping to a building and connecting up a ground source heat pump. But that doesn't have to be the only way that you receive or reject heating energy in a community. Once you've built out a thermal energy network, now you can start doing some creative things, like maybe we collect some heat off of the back of solar panels. We put that into the network, we store it underground in the boreholes that are connected to the system, and we've just reduced the amount of drilling that we need to do. Maybe there's industrial processes nearby. Maybe there's a way to reject heat, something like a swimming pool that needs heating energy deployed into it, or something like irrigation systems on a university campus or a golf course, or something that uses quite a bit of water for irrigation. Those are all thermal assets that can be interconnected into the network. And what that does is it increases the efficiency first and foremost, because that thermal energy is no longer being wasted, but it also reduces cost, because geothermal boreholes are great. They perform well. They do come at a cost premium. It's not generally very cheap to drill 600 or 800 feet down vertical into the ground. And so the more you can leverage alternative thermal assets, the more economical your project can potentially be. I don't have a photo of it in my slide deck here, but one thing I always encourage folks to do if they're ever in a colder region and you get into a downtown urban area, or especially a big city like New York or Boston, where I'm from, if you walk around on one of the cold days in January or February and look up at the tops of all of the buildings, you see thermal energy being rejected everywhere. Doesn't really matter why it's happening. The point is, people would rather release that out into the air because they don't have anywhere else for it to go. They don't have a thermal energy network to potentially deploy it into, or even sell it if you have a utility or some kind of a thermal operator running the system. So once these networks are established, you get all kinds of interesting ways that you can move energy through the community rather than just reject it out into the air, as is typically done. As I said, I did really quickly want to touch on heat pumps and sort of how they fit into the picture here. Hopefully folks are generally familiar with a heat pump, but heat pumps are everywhere. Everybody's got one in their homes. Your refrigerator is a heat pump. An air conditioning unit is a heat pump. So not new technology. The new and novel thing here is just how it's deployed. When they're used as a ground source or a water source heat pump, the efficiency is extremely high compared to something like an air source heat pump or an air conditioner. The reason is because of the temperature range that it operates in. Heat pumps are typically happiest sitting right at about a 60-degree medium that they're operating with. So if you're thinking an air source heat pump or an air conditioner on a 60-degree day out, it's running really efficiently. It's probably producing 3 or so units of energy for every 1 unit of electricity that it consumes. The challenge with them is, especially in a climate like the one I live in, you get into the winter when it's 30 degrees outside, 20, 10. Now all of a sudden that heat pump is trying to pull thermal energy out of that 10-degree air, push it into a building, and the efficiency drops accordingly. So you get very low 1.5 times efficiencies in the cold winter or the middle of the peak summer days. And that's because of that thermal gradient that has to be overcome. With ground source heat pumps, on the other hand, you're typically operating in that nice range from about 35 degrees to 75 degrees. So what that means is, on average, they end up being about twice as efficient as a comparable air source heat pump, and a little more efficient even then than something like a standard central air conditioning unit that folks would have on their home or their building. So how do those heat pumps go into buildings? Every time I give a presentation, one of the first questions that I get is, or comments sometimes, is people will look at the slide deck and say, yeah, that's great. It works in Massachusetts with your buildings and your systems that you have here, but it doesn't work in my community because our buildings are different. And I don't need to sit on this slide for a long time, but I just want to reiterate that this technology is very flexible, especially from a building standpoint. There are ways to get systems into single-family homes, apartment buildings, commercial buildings, you name it, and there's a way to deploy a ground source or a water source heat pump into the building. Sometimes you need to get a little bit creative. You may need something like VRF, which is a variable refrigerant flow, a mini split system in some homes that just can't physically accommodate ducting, but it's possible. There are ways to do it. And we demonstrated that on the project that I led in Framingham, which I'll talk about a little bit now. That project was a community deployment of one of these systems. So you can see here on the right, there's a continuous 1-mile circuit of pipe that runs in kind of a square throughout the community. We connected up 36 different buildings, and that was a mix of everything from single-family residential homes to low-income multifamily apartment buildings, and then some municipal and commercial buildings as well. So every type of HVAC system that you can think of. And I ran into any and every challenge on those building conversions that you can think of. Undersized electrical panels, lead paint, mold, asbestos, knob and tube wiring. If you can think of an issue that you have in a home renovation, I probably dealt with it on this project. But at the end of the day, we successfully got it in. The customers have been on and running since about last summer is when we started the pumps up to run it. And the whole thing is being fed by 90 boreholes down into the ground. In Framingham, we went 600 feet vertical on those holes. But looking towards other regions or other projects in the future, that would be dialed in for your specific geology and your specific loads. So taking a little bit of a step back and talking about the value proposition of a system like this, why did the utility look at deploying a thermal energy network at all? And I like to break it out into three separate categories here. The first is to look at it from the customer perspective. For customers that participate in a project, a pilot, a system like this, there are a few notable benefits that we like to flag. The first one is, generally speaking, these are the lowest cost systems to operate. And I like to caveat that a little bit because this is before you take into account something like a geothermal service charge. But if you're just comparing the electricity to run a ground source heat pump to the electricity to run an air source heat pump to the cost to purchase natural gas, delivered fuel oil, propane, you name it, on average across a year, the geothermal system comes out as the lowest cost to operate. And that rolls into things like maintenance and longevity as well. The systems are very simple to maintain. You basically change filters on them, and they usually last upwards of 30 years on the equipment compared to some of the alternatives like a gas furnace or an air source heat pump that may be in the 15 to 20-year range. The last benefit that I like to mention, and this is a big one, or it was for our project, is that central cooling comes along with it. So rather than just replacing your heating system, you're getting cooling along with that same unit. And especially in the Northeast where I live, that's a huge benefit. Many homeowners are relying on window air conditioners. They've never had air conditioning throughout their entire home. And so when you come and speak with them and say, we're going to replace your old furnace or boiler, we're going to put this new system in, it's going to be simple, easy to operate. Oh, and you're getting air conditioning with it. That was what really sold them on it. Depending on where you are in the country, air conditioning may be a normal and deployed everywhere or a requirement in buildings. But it's also a cheaper to operate air conditioning system. So the benefit is still there for the customer. From the business standpoint, or the utility, municipality, energy company, whoever is owning and operating the system, there are a few benefits to list out as well. First and foremost, these are generally long-lived assets that are going into the ground, so it fits very well with a traditional utility model. The plastic pipes that are going underneath the street or the service lines that are being pulled to the buildings, those are the exact same high-density polyethylene that is put in for gas work today. So what that means is the utilities already understand it, they know how to put it in, and the cross-training is very easy and simple. In the case of Framingham, we brought out a crew that had been putting in tens of miles of gas pipe per season, and it was about a 1-hour training with the pipe vendor just to make sure they didn't have any questions and they knew exactly what they were doing. And they were off to the races putting the pipe into the street. So there's also that cross-skilling and that local workforce opportunity as well. The business isn't looking at, we need to retrain a whole host of our workers on this brand new technology. No, this is just a transition. They can be installing gas pipe on one day and they can come out and install geothermal the next, and it is relatively seamless. So that's a huge benefit for the business. They don't have to deal with that upfront training and challenge of what do I do with workforce? They already have it. The last point on the business category, and this was specific for us in the Northeast, but I would imagine applies in some parts of California and the region as well, is that there are areas that just simply don't have utility service right now. For us, it's folks that rely on delivered fuel oil, and that's about 40% of the customers in Connecticut and Massachusetts. So from the business standpoint or the utility standpoint, this is also an opportunity for a brand new business line to serve utility quality service to customers that otherwise would not be able to have it. So I'm thinking in this region, things like the end of Cape Cod that doesn't have a gas line and never will. They will never extend a line out to the end of the Cape. It's a prime area to go and deploy a thermal energy network or a geothermal system, connect up all of those customers on this super efficient, great performing system. And now you don't have to do fuel deliveries out there anymore. So a lot of benefits for potential territory expansion, business line development. It makes a lot of sense from that standpoint. The last category here, and this is one I really don't want to understate, are benefits to the general system. And what I mean by that is the utility and energy landscape writ large. Because of how efficient these thermal energy networks, or specifically these geothermal networks, are, you have a noted impact on the electric grid, as well as replacing usage of things like fuel, oil, natural gas, etc. So what you do is you end up lowering the peaks. The summer peaks come down immediately because of that high efficiency. And as you transition heating load over to the electric grid, it's much lower and much more stable. So what does that mean at the big picture level? What that means is huge savings on things like electric grid build out. The Oak Ridge National Lab did a study, I believe it was last year in 24, it may have been end of 23, where they simulated what it would look like if a healthy portion of the nation transitioned over to geothermal or ground source heat pumps as their primary heating and cooling source, and what that would mean for an energy transition to decarbonized systems and solutions. And the savings were massive. They were predicting on the order of trillions of dollars of avoided capital expenditure on new power generation, transmission lines, distribution equipment. That's all going to be needed if we're going to meet decarbonization goals. You just need to do less of it when you're using a more efficient system. So you have knock-on effects for the electric grid. You have decarbonization at the utility and the neighborhood scale. And you have a lot of mitigation for potential build out into the future, which should translate into lower utility rates, or at least the utility rates not going up as quickly as they have in the past. So that one's a little bit of a hard benefit generally to quantify. Looking at it at the national scale and then dialing down into the local area can be difficult, but it was one that I was actively working on towards the end of my time at the utility, and that I'm still looking at today, because as you consider the benefits versus the costs of a system like this, if you don't take into account those peripheral benefits, you're not painting an accurate picture of the whole system. One final thing to talk about, and this one is important going back sort of to that business case value proposition, is that these systems are also expandable. So once you've put one in, if you see here in red, that was the root of the original Framingham project, you can actually build onto them almost like Lego blocks. You're not set with just that existing system, and that's all of the customers that you will ever have connected to that loop. You can tack on a sub loop, put a little bit more pumping infrastructure in, maybe you do a little bit more drilling to support those new customers. But the point here is that it's much simpler, and more importantly, it's much cheaper on the second iteration. So with Framingham, we had designed and we were in the process of building the initial system when we applied for a DOE-funded grant to design an expansion on Framingham. We were the first utility in the nation to do it, and we were the first to propose an expansion. We ended up winning that grant, and that black loop on the left is what that expansion proposed looked like. We were approximately planning to double the capacity of the system. So we were going to go from 375 tons of peak load to about 800 tons of peak load with the second iteration, but we were going to do it at approximately half the cost. And so as I was speaking to leadership within the utility and talking to stakeholders in Massachusetts and other people in the industry, the point I was trying to drive home is the first iteration may be on the expensive side when you put the very first loop in, but as you build these and as you expand them, the cost per customer comes down, and that's where you really reach utility scale. And by the way, that's not unique. That's how the utilities were built out way back when. People have just forgot about it because we built our gas systems, for example, 150 years ago, at least in the Northeast, that's when they were built. There was that initial capital expenditure or that initial investment in the community that was made, and we have since built on that like Lego blocks over time, and that's how we arrive at the energy costs that we have today. If you go back and look at a totally greenfield site and compare the costs today, and I think I have a slide on this a little bit later, of a brand new gas system, connection to the transmission lines, gate station, distribution, all of the components that go into it, and you compare that to a thermal energy network or a network geothermal system, they're pretty comparable. And so it's really wrapping your mind around this is a new utility versus this is a one-off project and here's the cost per customer, I think is an important thing to include in the conversation. Kind of continuing on that, here's a cost breakdown of what the first iteration of the Framingham project was to the second iteration or the planned expansion. And you can actually see how the building conversions, which are the dark blue piece of the pie chart there, start to really take over the budget. And that's because you need to convert the buildings one way or the other, especially if you're in an area doing retrofits. And so as you save money on the bore fields and the civil work and the pumping infrastructure that you've already got in place, the building conversions start taking up a larger and a larger portion of your overall budget. But that being said, we still were projecting 40 to 50% total budget reduction on that doubling of the overall capacity. This slide is that apples to apples comparison that I was talking about. It also includes a comparison of annual heating and cooling costs down below that I was speaking to earlier when I said that geothermal tends to have the cheapest operating costs of any of the options on the market. My little asterisk there below the table is that, yes, these are based on Massachusetts loads and Massachusetts utility rates. I think I ran these last winter, but it's a relatively easy exercise for your local region to come in and say, here's my electricity cost per kilowatt. Here is my, gas cost per therm, oil cost per therm, propane, and you can plug it into a calculator very simply. One thing to note here that is probably California specific, I'm actually not sure on this, and maybe we can get into that in the Q&A, but my understanding is that time of day pricing is something that exists in California that we don't have here in Massachusetts. That introduces actually a really interesting opportunity on a system like this where you can leverage using energy at times of day where it's extremely cheap to precondition your system, and then you lower loads during times of day where the prices may be higher. So what does that look like practically? On a system like the one I have in Framingham, maybe I throw a dry cooler or a large air source heat pump onto the system, and I wait until it's the lowest energy cost possible, and then I kick it on and run it to pre-cool the system. I can bring the temperature down in the water and underground, and then I turn the thing off and ride through the peak. And that allows me to arbitrage the time of day because I have a thermal storage system that I'm connected to. So something that would be also worth exploring if you were to consider a system like this and you were running the economics is, can we potentially leverage that opportunity in our utility market? So wrapping up on the overall kind of utility cost model here, these systems make a lot of sense for the utilities from a rate-based perspective as well. What we've looked at doing in Massachusetts and conversations that I've had with utilities kind of across the nation are the potential opportunity for blending rate bases with gas utilities especially. Now, at first, people generally stand up and say, why would you ever want to do that? And how would you be allowed to do it? Why would you have gas ratepayers paying for a geothermal system that they weren't benefiting from? And it's definitely a valid question. But the answer that I give is that this is what makes sense from a decarbonization goal standpoint. And it also makes sense when you start thinking about the problem that the gas rate base and the gas utility is going to have longer term. If we as a society begin transitioning away from using natural gas, you have all of these assets that are already in the ground. They're still being depreciated. They're still being paid for. But as customers leave that gas utility, you're spreading the same amount of cost over a fewer and fewer number of customers. Eventually, the gas rates are going to go up and the costs are going to get so high that people are going to begin fleeing the system and it will financially collapse. What if you were to stabilize it with a new geothermal utility that you were building out? So in the near term, yes, you may be subsidizing some of that geothermal cost across the gas rate base, but as you get to the longer term where the gas system is shrinking and it has less and less customers, you are now using that thermal utility or the geothermal rate base to stabilize the gas rate base as the final customers leave the system. So it makes for a much more predictable and stable rate model. And it's really one of the only proposed ways that I've seen to effectively transition off of gas. Otherwise, you're going to have to be going at very large scale very quickly and essentially telling people, we're turning your system off. You have X amount of time to get off of it. So figure out what you'd like to do. And honestly, my concern there is always that rather than moving to some kind of decarbonized solution like an air source heat pump or a ground source heat pump, customers will just choose to go backwards and get propane or fuel oil, which will actually increase emissions. So a utility model allows us to move at the network level, at the district or the neighborhood scale, and also stabilize the rate base so that we can make a smooth and seamless transition. The last bullet points on this slide to point out are there are actually a lot of existing skill sets and groups within a municipality or a utility that can translate very nicely over to these systems as well. When we deployed ours in Framingham, using things like the billing group or the GIS and mapping team, the sales team, these were trained existing workers within the utility that picked up geothermal very quickly and were able to be leveraged on the project. Whereas if you were standing up your own geothermal utility or company from scratch, these are all things that you would have to think about. I've had quite a few conversations with municipalities, both here in the Northeast as well as outside of the region, where they say, we love the idea, it sounds great, we're willing to fund it, we'll find the funding, let's get the pipes in the ground, but we don't want to deal with operating it. We don't want to think about how we bill customers and how we maintain maps and how we go out and make repairs and how we do metering and monitoring. That all sounds like a headache. Whereas for the utility, that's every day. And so adding this as another business line or a tool in the tool belt may make more sense than trying to develop it all from scratch. The last point there, fixed pricing contracts. That's an interesting one from the contractor and the workforce standpoint. And what I was really trying to highlight is that the utilities already deal with large construction projects. For example, the one that I worked for, Eversource, puts in about 100 miles of gas main every year. So there are existing relationships and contracts with the companies that do that effectively. And generally, they can get the lowest price per foot to put these pieces of plastic in the ground than anybody can. And so those relationships and contracts can be leveraged for geothermal work as well to make sure that you're doing it at the best possible cost and saving ratepayers as much money as possible. So what does the industry momentum look like? This image here is a screenshot of a utility collaborative that is working on network geothermal projects, or at least meeting regularly to discuss them. In green, you can see the states that actively have pilots up and running. This map seems to change by the day. So unfortunately, we don't have any of our fellow California utilities participating yet. But honestly, from the time that this screenshot was taken to now, that may have already changed. So what I like to highlight here is that this isn't just a niche thing in the Northeast or Massachusetts especially. There are utilities across the country that are thinking about these projects, that are actively evaluating them as an alternative to traditional gas service, up into Canada, and then actually across the world as well. You can see here on the bullets on the left, I'm actively working on some projects in Central Asian countries that are looking at doing this on the 20, 30, 40,000 unit scale. There are examples of projects across Europe, Asia, Australia, New Zealand. They're being deployed. So there's a lot of momentum that is building right now, and it feels like everybody is just on the cusp of understanding the concept, understanding the technology, getting comfortable with it, and then taking that step into, okay, let's put some pipe in the ground and actually demonstrate that we can do this here in our region, cities, towns, states. So on that note, what makes a good location? And I added a couple of slides here towards the end of my presentation to kind of dive into some specifics on your region, on the Truckee area and kind of the Tahoe climate and why it may or may not make sense to deploy a system like this. But taking a little bit of a step back, how do you even evaluate an area for a thermal energy network? And, the 3 bullets that I put there are kind of the key critical factors to a successful project. There are all sorts of other screening criteria that you can include in an analysis. You can see below, these are some of them that we considered in Framingham. But from a technical perspective, the things that you really care about are, do I have enough available space for bore fields? Do I have any kind of load diversity? Is this an area with some commercial buildings, maybe a school or municipal buildings, as well as residential homes, whether those are single family or high rise, low rise? And then are there any other thermal resources that I can take advantage of to balance my system? Because the systems perform best if you have a more or less equal heating and cooling load. Unfortunately, there aren't a ton of regions across the United States that the heating and the cooling load is balanced all on its own. If you look at buildings, they tend to be one or the other. In your region, I believe you're a little bit heating dominated. It's actually pretty close, which is a good thing, but you can use those other thermal resources to balance the equation, so to speak. In Framingham, we had an interesting situation where the residential homes tended to be heating dominated on an annual basis. The commercial buildings tended to be cooling dominated on an annual basis. So those were the two levers that we could pull. We looked at what our loads were, and then we added or removed from one side or the other of the balance until we got to a point where we were annual on a net basis flat. And what that means is we won't change the ground temperature over time. In the winter, it'll go down a few degrees in the ground. In the summer, it'll come back up a few degrees, and it'll do a nice, easy season over season up and down shift so that in 20, 30, 40 years time, the ground temperatures are the same as they were on day one, and the system performs the same as it was modeled. So in your location, as I said, from a climate standpoint, things are actually pretty positive. You have reasonably cool temperatures in the winter, but not super extreme, minus 20s. And then you have reasonably warm temperatures in the summer to kind of balance that out. So some quick looks that I did, it's slightly heating dominated, but that's not necessarily a problem. Commercial loads honestly may be able to balance that out the same way that they did here in Framingham. Water consumption is another interesting thing about the region. For us in Massachusetts, not nearly a concern as it is, out in the West, because we don't have water restrictions and our water prices are generally pretty low. But if there is existing cooling that is being done via evaporative cooling, which is primarily how large commercial outfits will run their cooling systems, that can actually be reduced pretty drastically. An example I like to give of this is Colorado Mesa University, which has one of the oldest network geothermal systems on campus in the country. They saved an amazing amount of water just by converting over to ground source heat pumps. So they hadn't actually planned for that initially. They were thinking through on a electricity savings and making their buildings very efficient. But then they noticed that the monetization, I think it's on the order of a few $100,000 a year in water savings that the university sees, was something to be definitely considered, especially if you're in a region where that's a challenge. Final point here, within the community, you have some interesting sources and sinks as well. I mentioned earlier in the presentation that golf courses can make for great areas to do heat rejection. So if you do end up a little bit cooling dominated because there are a lot of commercial buildings included, that's a great way to pre-temper the irrigation water. So you warm it up a little bit early in the morning from the loop, and then you put it through the sprinklers as you would normally, and that allows you to reject a lot of heat out onto the grass and balance your thermal loads. So it's a very cheap and effective way to get a lot of additional capacity out of a system. You also may have things like breweries, bakeries, other businesses in town that generate a lot of heat that you could potentially capture and then reject out into the thermal network. And the great thing about that is, rather than getting it from underground, you put it into the pipes, you move it up the street, and a residential home may be able to take those BTUs and put them through their heat pump and deploy them back into their building. And the efficiency there is extremely high. When the systems are running in that fashion and you're exchanging energy, you can see coefficients of performance, which is a measure of that 1 unit of electricity in to 1 unit of heating or cooling energy on the outside. You can see them as high as 7, 8, 9 in some cases if you're simply pumping water up the street and exchanging heat between customers. So it makes for some very efficient and very interesting systems. So I believe this is my final slide here on the content, which is what are the initial steps that I see being taken for communities, for areas that are looking to undertake potentially exploring this technology. First and foremost, they tend to be things like feasibility studies. So we did a number here in Massachusetts. Towns and communities actually applied for some grants that came through the Mass CEC, which is a state organization, and they did feasibility reports to look at those factors that I talked about earlier. Do we have the space? Do we have the right load mix? Do we have the right building mix? Where in our community would it make sense to potentially deploy these, that we would have the best chances of an effective and economic solution? And then you can kind of put pen to paper and just start thinking through potential sites. You say, well, maybe the local school is a great anchor building that we could use. And so you start looking around the school and figuring out, okay, could I create a network around that? Maybe the airport has great open space for bore fields, lots of parking lot areas that you could drill underneath. Maybe we could use that as an anchor tenant and start building a network out from there. So really looking at what would make sense within town, and where does it make sense to stop? So this is something that I didn't mention earlier in the presentation, but there generally is a logical endpoint to these systems. Once you get far enough separated between homes or buildings, the economics of pulling pipes down 1, 2, 3 miles of road to get to the next customer, they just don't make sense anymore. And so you really then look at what are the logical boundaries for a network, and try to avoid trying to expand into an area that you're not going to be able to do so in an economic fashion. Maybe that means you stop and you move to the next town and you start another subloop there and start working from their downtown or their anchor tenants. But it is something to keep in mind that I like to say thermal energy networks, geothermal, they are a great tool in the tool belt. I would never say that they are a one-size-fits-all solution for anywhere and everywhere. So you need to be a little bit diligent and logical about where you think about putting them in. And then the final bullet point here is on regulatory and legal groundwork. There are generally some questions that need to be answered about who is the logical ownership entity, whether that's the local municipal department, water, sewer, DPW, or the local gas utility or electric utility, or a standalone entity like an ESCO that could own and operate these. I mentioned some of the challenges to that approach, but it's certainly one that works in some places, most notably Europe. They're particularly popular. And then finally, do they have the legal requirements or the legal permission to operate a geothermal service? In Massachusetts, we just had recent legislation that changed that for the gas utility, making them thermal utilities that are now able to provide that type of energy service to customers. But it's definitely worth looking into in your local area and region to make sure that it's something that you can even legally do. I know in Connecticut, the initial response that we got was, you can't do that. We can't find anywhere in the law that would allow you to do it. So you need a legislative change before you can do geothermal projects as a utility in Connecticut. I know California had some legislation that was passed recently. I'm not sure if that fully opened the door for utility ownership or not, but it's something I can definitely check on. So with that, I just wanted to thank everybody for joining today and listening to my pitch here. And, my company, Thermal Energy Insights, up here on the screen. Certainly happy to help and support however I can.
Thank you, Eric. That was very informative. You did such a good job covering the questions that we had that I had to generate some more because you answered a bunch. Let's see. I'm curious. This is just a sort of a technical question, but what happens to the bore well pipes after their 50-year lifespan ends? Can they be removed or replaced without leaving the old pipes in the ground?
Great question. The short answer is you shouldn't need to. I said 50 years just because that's the general agreed upon timeline for things like buried pipes in the street, the mains and services. The reality is the ground exchanger could last 100+ years. These are totally static pipes. They don't have any fusions. They don't have any joints. It's a continuous run down and up, and it's grouted into place underground. So short of the actual plastic resin breaking down over time, which if you've ever seen one of those charts on how long it takes plastic to break down in a landfill, those aren't really going anywhere. So 50 years is kind of a industry agreed upon official lifetime. The ground exchangers could last 100 plus. So I wouldn't be too worried about it. If in the event that they did break down or need to be replaced, there could potentially be ways to pull the old pipe, remove the grout, and re-grout and install. It may be a little challenging, and honestly, it might be economical to just move over to the side 10 feet and drill a new hole. So it would be something to evaluate, but I'd be thinking of it on the 100-year time scale, not the 50 necessarily.
Great. So you mentioned, for instance, if buildings were, say, a mile apart, that, the economics of it might break down. So if you were doing a feasibility study, presumably you have some sort of model that allows you to determine whether, you've kind of hit that distance. Is that something that's sort of built from scratch, that model, or is that something that exists out there in the world and you can pay for access to it? Does it work off of GIS? How does that work?
I'm not aware of any existing software solutions, for example, that allow you to very easily kind of plug it in and it says yes or no on the economics. Honestly, my approach would be probably to just look at it on a dollar per ton of capacity standpoint. So you know how much it's going to cost you to put a foot of pipe in. You know how much it's in pumping energy every foot is going to add. So you can pretty quickly add up and say, hey, if I'm moving 30 feet down the street to my neighbor in a downtown urban area, that's pretty straightforward. If I'm moving a mile, I need to run a mile of pipe to the tune of $1 million plus the pumping, et cetera. You can pretty quickly see an inflection point where it doesn't make any sense. And that's going to line up very well with the overall density of the city or town. You can almost go on to Google Maps and look and see where kind of the edges of dense development stop, and that's going to be your logical endpoint.
Makes sense. So Heat, the nonprofit that Eversource worked with on this project, when they were originally looking at this concept, they had identified streets as the location for bore wells, whereas Eversource implemented the bore fields in a concentrated area. Can you just speak briefly to why Eversource chose that option over drilling in the streets?
Yep, a few reasons for that decision. The streets are interesting because when you first think about it, you look at the streets and say, ooh, there's a lot of great space that we can use to put bore fields in. When you come at it from the utility angle and you start thinking about something like downtown Cambridge, all of a sudden the street looks very unattractive. We have trouble opening the street up just to make a repair without hitting other utilities in downtown Boston. And so the congestion and using that real estate tends to be somewhat challenging. That's one factor to it. I would honestly be worried about the assets getting hit if the city or town came in to do a sewer main replacement or a water line extension or any of a number of reasons to dig in the street. Those bore fields would be prime for getting tagged by an excavator. They're a little bit safer off the street underneath a parking lot or a ball field, or even in some cases, the foundation of a building. I didn't mention this in the presentation, but there are some great projects that have taken place in downtown New York, for example, where bore fields have been drilled under the foundation of a new building, and then the building was built on top of them. Or in one case, they went into the basement of a historical church and drilled geothermal ground exchangers in the basement with a small little rig. So you can get very creative about where you put these boreholes. They don't necessarily have to be in the street. And I think that the street opens you up to a number of additional risks. And that's before you consider things like the traffic disruption. People get upset enough about you laying plastic pipe in the street where you're there and gone in about a day. If you're sitting there and drilling boreholes for a few months, I think the local community may be coming out with torches and pitchforks. But maybe they'll be understanding. I don't know that I would want to be the one on the rig, though.
Yeah, fair. That makes sense. So, for instance, you mentioned a golf course or a brewery rejecting heat into the loop. So, in a system like that, would you have a meter on their access point to the loop so that they could measure the BTUs that they're sending into the system? How would they get paid for the BTUs that they're rejecting?
Generally, yes, that would be the way to do it. Even if you came to some agreement on a flat fee, for example, you calculated, hey, the brewery runs X number of times a week. They tend to reject Y BTUs. We'll pay you Z dollars per month to put a heat exchanger on your system and pull that heat off. You'd still want to verify that they were actually delivering what they were agreeing to. So on any kind of, for lack of a better term, net metering agreement, you would always want some form of BTU meter to measure what you were actually getting. The other thing that would do is it would also prevent you from taking heat when you don't want it. So you don't want to be grabbing that brewery heat in the middle of summer when you're trying to cool everybody on the system. It's going to actively be detrimental to the performance of your loop. So you need a temperature sensor there, both in the loop and on whatever that commercial customer is, to say, first and foremost, do I even want this energy? And then you say, okay, yes, I want it. Here's how much I took. And you could compensate appropriately.
Great. Let's see. Can you just briefly touch on what is the financial model for a thermal energy network? Is the cost shared across all customers as if you were doing a pipe replacement? Did Eversource pay for upgrades necessary to participants' homes?
Yeah, so on the Eversource project, the costs of the project were distributed across the gas rate base. So essentially, we looked at the project costs and said, the point here is a demonstration. We want to show that, yes, the technology works, and yes, the utility can do it. So we're going to take it, distribute it out as if it was any capital project for the gas company. And we charged the customers a very low monthly fee to participate. And that was more for a billing relationship. Looking larger picture or towards the future of what it may look like, you could have some sort of capacity-based service charge. So you look at what the cost of a project is, what the return on investment needs to be, what the operating costs are. You roll all of that up into some kind of a revenue requirement. And then you say, we're going to divide this evenly among the participants based on what percentage of the capacity they use. So if you have a 300-ton system and you got a customer that has a 3-ton heat pump, they get 1% of the overall requirement. Whereas if you have a big commercial customer that's, maybe they're 10% if they're pulling 30 tons. So that's one way to do it. The other is to actually meter every single customer and charge on a per BTU basis. There are examples of projects up in Canada that do that. Personally, and this is just my opinion, I would never want to maintain meters if I don't have to. So if I could come up with some predictable flat rate fee, that's the route I would go down 10 times out of 10, because having equipment that you need to maintain, you have accuracy standards, you have to come up with fee changes all of the time. I don't want to get into metering if I don't need to. And I would advise anybody, if they can come up with a way to not meter, don't do it. The one exception is those commercial customers. And sorry, the last part of that question you asked about, yes, the building conversions were included in the budget in Framingham. So it was everything from holes in the ground to heat pumps in the homes. The idea there was to make it as easy as possible for customers to participate.
Great. And so, as I mentioned, the nonprofit advocacy organization HEAT was involved in this project. Can you just summarize what their role was, and what's your feeling on how helpful it was having them involved? So, for instance, if there was, a situation that, if we were developing something like this in the Truckee Tahoe area, how helpful is it to have, an advocacy group sort of helping out where possible?
Yeah, and apologies, I do have a hard stop here in a few minutes, so I'm going to have to jump. But to answer on HEAT's role in advocacy, they were great. They were very instrumental in helping to introduce the technology to all of the relevant stakeholders. So they do a lot of great work talking to legislators and people in the municipal government and really bringing people together to discuss the technology and the benefits and why it makes sense to do a project like this. So once it got into actual technical project implementation, design, construction, et cetera, the utility picked it up and kind of ran with it. But they maintained their role as, advisors and community partners, and also did some research along with the project where they started looking at things like underground temperatures and performance of the system. So I would highly encourage folks to speak to them, learn from them. They are very knowledgeable and they're very good at bringing people together to, discuss these systems and make progress on their deployment.
Well, thank you, Eric. I think you've done an amazing job covering a huge range of topics here related to thermal energy networks. Thank you so much for your time. I'm going to respect your time and that of our audience. And thank you. And maybe Kaylee wants to jump on to close.
Yeah, Eric, thank you so much. This was incredibly informative and really appreciate your expertise. As you all know, this has been recorded and it should be up on the CTA website within a week at least, and we will follow up with everyone registered with the link to the recording. Thank you so much for joining us. Have a good afternoon.
Thank you, Eric.
Thank you, Eric.